Hello everyone and welcome to another Würth Elektronik eiSos webinar. My name is Markus Eberle and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar today. The topic of today's session is electrical contact resistance. Our speaker today is Florian Mohn, who is working as field application engineer in the field of ICANN at Würth Elektronik. And he will hold today's webinar and also answer your questions. So before we start the webinar, I would just like to point out a few things about the webinar today. So the presentation will be about 35 or 40 minutes long, and then after that we have scheduled a Q&A session, and we have scheduled for that around about 10 to 15 minutes for your questions. So if you have any questions, you will be muted during this webinar today. So that means that you cannot ask these questions via microphone. But nevertheless, you have the opportunity to ask us the questions via the chat function. You will find the chat function in the control panel. After the webinar, we have scheduled the time for the Q&A session, and we will go there through your questions. And if we don't have the time today to answer all your questions in the live webinar, we will answer them via email after the webinar. So all of your questions will be answered. Then just also the other information at the end of the webinar, you will be asked to participate in a feedback survey. Of course, we would be pleased if you take the time to participate in the survey and help us to improve our webinars. After the webinar, in the next few days, you will also receive the link to the presentation as well as to the recording of this webinar. And yeah, you will get the links for that. So now I will hand over and thank you. And yeah, we'll hand over to Florian and wish you an exciting webinar. Thank you and have fun.
So thanks a lot, Markus, for the introduction and for sharing some information about the webinar itself. I hope all of you can see the presentation already. Just launched it, and yeah, welcome you and thanks a lot for participation. So I think let's get started. Everything was said right in the beginning about the time and so on. Maybe some introduction why that electrical contact resistance is important for us. Here we've got some bad examples what might happen or could happen in the worst case scenario. So first of all, in the left side of the picture, you can see some corrosion that occurred during time. Copper is a material which interacts quite easily with oxygen. And on the other side, you can see some termination that was caused by some lubricant that got dropped on the material itself. It was some cleansing material and caused that bad connection during the time. So the agenda for today is to give you some idea about the importance of the contact resistance itself. We will have got a closer look on wide board connection and the different resistances that occur here. In the next chapter, we have a more closer look about the raw materials, about connectors and so on. Also the platings, more specific examples, especially about coaxial connectors, red cubes, and also later some manufacturing processes which are inside the presentation. So first of all, maybe to highlight the importance and why the contact resistance plays such a big role. What you can see in that formula is that there's a square function inside the formula about the current rating. That means if you double the resistance, you have got also a doubling in the on that side, on the left-hand side, the temperature rise and also on the other side, what you can see here, also in the power losses. And for many connectors, especially when it comes up about current rating, also power losses are a big issue. But also, if you think about I/O connectors, here is an example from a USB-C type connector. Also here we've got the same phenomena, and in this case, these are the power losses and also voltage drop that you need to avoid to get a good connection and good data transfer. And that is also a reason why a good connection, good interconnection, and a low contact resistance is important to have. So we will have got a look inside the data sheet right in the beginning. Here is an example of one of our connectors, which is called mini module series. The defined contact resistance is 10 milliohm. In this case, these values always given in the data sheet is the contact resistance after the defined durability or mating cycles. That means in this case, 25 mating cycles are applied. You've got some contact which scratch over each other during that mating cycles. You've got a normal increase, slightly increase of the contact resistance. Afterwards, the values are measured and defined. Honestly, it's a very, let's say, high security margin that you do have got inside that measurement and or the mating cycles, which we will also see later on. What else we do we have for all of our products? We have got reliability reports that we can offer to you or send to you if you have got some interest more about vibration tests, salt spray tests, and so on. These are also an important aspect here about reliability and durability, especially vibration and salt spray tests are tests which are performed generally to our products. It's a defined standard behind. Additional influence you have got for humidity and also for temperature cycling. Therefore, you test the working temperatures where a connector is specified for. In this case, it's -40 up to 105 degrees Celsius. And perform afterwards also the contact resistant tests. So having a look on the contacts inside or the resistances inside the connection or a connector, we've got a couple of them. In all, these are 6 types of resistance that create the entire contact resistance. So first of all, which is shown over here in this white board connection, is of course the wire that you have. In these examples, it's 50 millimeter wire that got applied to the connector. Afterwards, we do have got the crimp resistance or the crimp contact itself. Afterwards, the raw material. The raw material, you've got 2 of them. First of all, the crimp contact, and on the other side, later shown, is also the pin connector inside the housing. Then you do have got the contact zone, which is quite an important thing. Therefore, there you have got the number of mating cycles that you can perform with a contact zone. I will also show you later on what's behind that. As already said, the raw material of the pin, and last not least, you do have got the soldering joint of the PCB or of the connector to the PCB, which also needs to be good. And in all, you've got the entire contact resistance RC, which is given over here. So the reason we do have got a little aspect of each of these contact resistances, first of all, about the raw material of the cable, which is given over here. One thing that I need to mention is the IACS, the International Association of Classification Societies. Here you can see, first of all, it's more about copper that is relevant for conductors. Raw material or pure copper is used in many cases. Next to that is given silver. You can see that regarding the metal conductivity, silver has got a slightly better rating in comparison to copper. But due to the fact that we're talking about conductors or wires, we've got a highlight or a closer look about conductor itself. Even gold has got a worse conductivity in relation to copper. Of course, a much higher price. So you do not make conductors or strands out of silver or gold, of course. So also here, I want to show you that in comparison, eiSos, we've got a look about the copper. We've got here the 100%. Later, you will also see the conductivity of silver, which we use for some of our products. And also gold, as we said, it's around 77% in comparison to copper, where we've got a closer look on. So the first value or the first resistance that we have is around 0.7 milliohms, what we can calculate, or 700 microohms. Up next, we've got the crimp connection. Crimp connection is a gas-tight interconnection of the cable with the crimp contact itself. We say it's a gas-tight connection. Gas means that no gases, especially oxygen, can get into that crimp connection to increase the contact resistance. That is a very important point. So a good good connection, good crimp connection is an important thing to have. Up next, of course, inside the entire process, only the harness maker has got an influence on that. It's also some aspect, you can see it here marked in red, within that contact resistance of the 10 milliohm, it's already integrated. Last of it, we have got a look on the solder connectivity, solder connection, sorry for that, under point 6 was mentioned in the overview. What you can see here in that chart is that tin has got a mere not such a good conductivity. For tin, we've got in comparison to copper around 15% what we can estimate about the metal conductivity. The explanation why tin is used for electromechanical components during the soldering profile, it has got a, in comparison to the materials that are shown over here, the lowest melting point. So that is the reason that even if metal or tin has got a very bad interconnection, tin is used in general for solder connections. So about the solder joint, we have got around 0.5 milliohms. And now we come more to the contact zone parameters, where we do have got the biggest influence as a manufacturer of components. First of all, we have got a look about different materials that are used. Most copper alloys that you can find is brass, but also bronze that you can find. In the first glance or in the first step, you can see that in comparison to pure copper, the metal conductivity of copper alloys is worse. So around 30% for brass, copper beryllium also 30%, and also for phosphor bronze, you have got only around 15% in comparison to pure copper. So you might ask yourself, okay, why do manufacturers have got these metal copper alloys? The reason for that is linked to the elastic and plastic moment of connectors. Connectors are components that you made and unmade during their life cycles quite often, and therefore also you need to take into consideration that you can meet the required mating cycles within a certain lifetime. And in this case, also you use copper materials, copper alloys, sorry, that have got a better elastic and plastic characteristic. So in this case, before the mating cycles, you've got 0.6 millimeter in opening. by the way, don't get confused. We have got here the after plug and unplugging. It's mentioned to have got 1 millimeter as an opening. The pin itself 0.9 millimeter. That was caused to a test which is also shown later on, where you do have got more mating cycles that were specified in the data sheet, and that explains also this widening of the contact material itself. So therefore, about the elastic limit, you choose copper alloys. In this case, if you compare the elastic limit, you can see that copper alloys and also phosphor bronze do have got much better values in comparison to pure copper. And that is exactly the explanation why we do use copper alloys, bronze, and also copper beryllium in comparison to or instead of copper, pure copper materials. That is an example, copper alloy for wire board connectors that we do have got in our portfolio. For example, another example is shown over here. That is the mini module series, which is specially designed for shock and vibration, and especially during or because of vibration, you choose a material that has got very good elastic limits. And therefore also bronze is used. Another aspect is linked to the relaxation, also a topic which is not that known. What is relaxation? If you think about contacts, that's a stamping and punching process where you create a certain shape of contact, and caused to this or due to this shape that you want to have, the material wants to go back to the original shape. So in first, the base material is delivered on reels. It's a flat material, and you're caused to punching during the punching process, and the contact gets formed. And over the time, and also by applying certain temperatures, you have got the relaxation. That means the punched contact wants to go back to its original shape, and therefore you use or you lose the contact force on the material that is shown over here. It's some kind of stress that you've got over the lifetime. In this case, it's shown here. Of course, temperatures are very high that you apply, normally about 150 degrees. You do not find in many applications, especially due to the fact that FR4 material, which is used for PCBs, it's also a limitation up to 150 degrees Celsius. But also 15 degrees is quite high. And you can see here in that chart that you've got at the end only after 100,000 hours around less than around 72-75% of the original contact force afterwards. So relation to the contacts that we use here for common wire board connectors, common brass is used quite often. Afterwards, the already mentioned mini module series, here the values are much better, and also latest shown the SMA connector, or in general the coax connectors that you can find here. We use the phosphor bronze, copper beryllium as a contact plating, and here you do have got the best value that you can find. So in the example of the raw material, we have got for the male and for the female side also around 1.6 or 1 milliohms. So that is the biggest impact on the entire contact resistance. Having a look on one aspect that many customers do not know or appliers do not know, we have got a look on the A-spots. What is an A-spot? even if you think about contacts, even if they seem shiny and very smooth, very even, if you've got a closer look, you can realize that the surface is not even or smooth at all. You've got some areas which are in higher positions, some of them are lower. What you can also see here in that cross section, the base material. Afterwards, you've got a more shiny area that is nickel underplating. The reason why we use nickel will be explained also later on. And afterwards, you can see the tin, which is applied as the surface. And that is exactly the reason if you apply two contacts on each other, you've got some sections which are lower and some sections where are higher. And within these sections, you create the so-called A-spots. And through these A-spots, if you apply the current or the voltage, the electrons flow. In between, you do have got these blue marked areas. That is some film resistance and also oxygen or air enclosures, what also increase the contact resistance and also might create some heat. So if you apply current, you do have got these resistances in between. Only some sections of the contacts are combined or attached to each other between the male and the female contact, and that also creates some contact resistance, some heat, and a reduction of the flow of the electrons. So having a look on the A-spots themselves, you can see in this graph, first of all, the number of A-spots, and on the x-axis, you find the pressure. That means the more pressure you apply with the so-called mating force, the more number of A-spots you create. But up to a certain point, that comes over here, you can see that these curves go in parallel to each other. It means it doesn't make sense to apply more force. More force creates a harsher connection between male and female side of the contact. That is more abrasion that you have, and this reduces the number of mating cycles. So here in that graph, you can see that you've got an optimized contact resistance, an area that you want to reach, and therefore you choose a material that can meet these required contact normal forces. So here we've got in addition an overview about the metal conductivity of the IACS. Copper is quite good. On the other side, you've got copper oxide, which has got a very, very low conductivity. As an example, copper backed interconnection creates also these mentioned contact loss, and a good example of copper oxide, which has got a very bad conductivity, shown over here, are things that you already know. If you bring pure copper to the environment, you get these oxidation processes, which are shown over here. It's more greenish and, as we said or have heard, a very bad conductivity. About the relative hardness, you can see tin is a very soft material, especially in comparison to gold. It's 50% less hardness in comparison to gold. But if you compare it also with nickel, nickel is used as an underplating. I just show it on the next slide. It is shown over here. Sorry, it's not shown over here or not indicated. For all of our connectors, that's something that we need to point out. Just realize that in the presentation, between the soft tin and the copper, you do have got the nickel underplating. And by using nickel as an underplating material, you increase the number of mating cycles. I hope exactly, sorry, my mistake in the presentation, it's shown over here. And that, not a mistake in the presentation, just a mistake from my side. Sorry, please excuse that. Hard nickel is shown over here to improve the number of mating cycles of connectors. Afterwards, you do have got the soft tin, and shown in black or in a very dark gray is the tin oxide, which needs to be removed by the contact normal force. And that explains also why we do use nickel as an underplating material. So about the entire contact between male and female side, you do have got 0.8 milliohms. That is also a margin, a very huge margin that we do have got inside. If you have got a entire comparison between that general contact resistance, which is shown over here, about 10 milliohms, in comparison to the real contact resistance that you have, you can see that the security of margin of our products is quite high. Some tests which were performed are mating tests, because the colleagues asked themselves, why do we specify our components in such a conservative way? You can see here in the green line the specified values with 25 mating cycles. Afterwards, you can see the 10 times multiplied by 10 times, that the contact resistance is even in a range around the 10 milliohms that got specified in our data sheet. And even beyond that, you've got a more increase of the contact resistance. So, of course, as we said, it's a security margin that we calculate, and also about the pictures that were taken, you can see here after these 1,000 mating cycles on the right-hand side, it's shown in a very good way that you can see here the pure copper alloy, which is shown from the tin. It gets removed. Also some tin oxide, you can see here, it's more not that shiny. It's dark gray material, but definitely you can see that you've got some reduction on top of the material. Especially when you think about wire-to-board connectors, in this case, which are used for current rating or for higher current rating. That is the MPC4 connector. The colleagues also had got a closer look on that. This connector is specified with 25 mating cycles, where you do have got very good values. It's a comparison of the temperature delta. You can see here you've got an optimum value that gets applied. Also with the thermo camera, you can see that for using 5,000 mating cycles, which is quite a lot, you do have got a very high increase of the temperature. That one here, which had around 5,000 mating cycles, was much higher with the maximum temperature that was applied, maximum current that was applied in comparison to the connector that has around 25 mating cycles. So factor 2.5 is given here between the standard connector, not standard connector, the connector with the 25 mating cycles in comparison to the one with a much higher mating cycles. So also temperature increase might be a critical aspect in this consideration. What also can another aspect that might occur is the so-called fretting corrosion. Fretting corrosion means if you do have got a two contacts that are applied to each other, you have got some fretting or some vibration that might occur during the time. What happens here is that the tin oxide, which is a normal oxidized process that you can find here on the contact itself. It's a very hard material. on slides, some slides before, you can maybe you think about that. It's a very hard material that gets between the pure tin over the time, and during the hardness of the material that you have, the contact resistance increases over the time, and it gets a very bad interconnection. So that is also some fretting corrosion that could be or might be also taken into consideration. Oxidation is also an important aspect. What is shown over here, you've got very low values, for example, for gold and silver, which do have got quite a good value. On the other side, you do have got iron as a bad example, where some oxidation or corrosion might happen very easily over the time. And that's also one aspect that you need to avoid. So there are also materials that are better, or some of them are worse. And also, if you think about the number of mating cycles for lower mating cycles, you use tin quite often. It's cheap material. Mating cycles are not that often. On the other side, if you have I/O connectors, for example, the plating material which you use or prefer here is gold plating. You've got less contact normal force. That is also shown here by this blue arrows for gold plating, less contact normal force for tin, higher contact normal force, due to the fact that you want to create more A-spots between male and female part. So as an example, in the presentation, you can find here some I/O connectors and also pin and socket headers where you do use gold as a contact plating. In comparison to tin, you've got a better value about the contact A-spot. On the next slide here, also some abrasion that you can see also here on the material. In this case, the mating cycles were around 700. Also, the contact resistance remains in a very similar way, or very parallel to the curve around these defined 10 milliohms. Unfortunately, the ohm sign got lost here, so we also need to add that. What can you also do to improve the number of mating cycles is to use palladium in addition to gold. And especially about USB-C types, where you have got a much higher number of mating cycles, which is defined by the USB organization. In this case, it's 10,000 mating cycles, which you need to have at least. Also, the colleagues make some researches here and performed 30,000 mating cycles. Also here, regarding the contact resistance, you can see that without any issue, you might have got these 30,000 mating cycles. Of course, the aspects you can also find here during abrasion or some fretting corrosion, which is shown over here. You can see some scratches also on top of the gold contact. The plastic also gets torn or gets removed and is attached on the contacts themselves. So also that's a point that you need to take in consideration. When you think about the switches, you have got two base materials which are quite often or more in use. On the left-hand side, you can see the switches which have got gold plating. Gold plating has got, in regard to the electrical life, less interactions or less life cycles, 2000 cycles that we have. In comparison, on the right-hand side, we can find some other switch products which have got silver plating. And silver has got the advantage that you have got more electrical life cycles during the time. And yeah, that is also a reason caused or due to the better electrical conductivity that you use silver instead of gold plating. Especially about the rocker switches that you can see here in the picture, you have got much thicker material, silver that gets applied to the contact material. Also a good example is shown over here. The material, what you can see over here, is pure silver that gets attached to the contact. You do have got very low contact resistance or very good conductivity. What happens always if you switch or if you switch a rocker switch under load is that spark that is created. Of course, it deteriorates in a certain way the surface. Yeah, it's also an aspect that you take in consideration. But also for these kind of products, yeah, it's used due to these thicker silver dotation that is used over here. A bit more, let's say, specific examples where these surfaces are used for some, or these aspects that we were talking about even before are used for some more specific connections or connectors. We have got in the first step a look on the high frequency connectors or higher frequency connectors. If you have got a look on this graph, for example, SMA connectors do have got the highest frequency rate of these coaxial connectors with 18 gigahertz. And you can also see that the gold plating or the gold plating thickness is the highest on these SMA connectors. The mating cycles of all connectors is the same, but the frequencies, especially in comparison to MCX, MMCX, SMB connectors, is much lower. But also the gold plating thickness is lower, and the reason for that we will see in a short while. By the way, also SMP has got a higher gold plating thickness and also here a higher frequency that it is designed for. First of all, we have got a look on the mating cycles also by applying or by mating this interconnection 1000 times. You can see some scratches and some deterioration on the surface, more double or 2 times more than it is specified in the data sheet. And the reason for that, sorry for skipping that slide before, the reason for that is that you have got the skin effect. Skin effect means that depending on the frequency you apply, the electromagnetic wave only goes to the surface of that of the material itself. And for 18 gigahertz, for example, the electromagnetic wave has a depth of 0.6 micrometer into the surface of the material, especially for high frequency applications. You want to have got low losses, for example, a very good interconnection, that you've got a very good data transfer. And that's also an explanation why for high frequency connectors, you should have take or use a very higher plating to get less losses in the interconnection. About the galvanic corrosion, that's the last point I want to talk about. You've got here an overview about the contact, about corrosion resistance. Gold and silver is quite good, and that overview here explains the combination of two materials when you do have got galvanic corrosion. Regarding I added one slide. Right in the morning, we had a presentation in German language and the afternoon in English. And I just wanted to explain that with a little bit of chemistry. That's how I call it. We've got the core. If you think about atoms, we have got the core, which is shown here in red. You do have got protons and neutrons, and in the shell model, you do have got certain shells afterwards on the atom model. And on the outer shell, you've got the valence electrons, and these valence electrons are adapted or attracted by some other atoms, and for some ions that you have, you might have got a deterioration of the surface of the ions which are applied on the contacts, and that is just an addition that I made. On the right-hand side, you can also see a copper atom. You only have got one electron. That also explains the good conductivity. Also, silver has got a very good conductivity, as we have seen. And here, these atoms do have got only one valence electrons. So going back to that slide, as we said, some materials have got the ability or the interest or the attraction of these electrons, and if you have got some combination between the materials, it might be critical. It's also a good explanation why we do use nickel as an underplating, because if you see here inside that overview or inside the chart, in combination with gold, stainless steel, which is used for tactile switches, silver, copper, brass, and also tin. Tin is here also in an area, in an acceptable area. It's a material where you can combine most of the contact surfaces. Exactly. So going further, the colleagues also made some tests. Here in that case, it's shown for some FFC connectors, it's a combination of a surface of tin. On the other side, you had a combination from male and female side, or FFC connector and FFC cable with a gold surface. The colleagues performed salt spray test for 144 hours. And what you can see over here, you do have got some indentations of the counterpart. That is not critical at all. You can see also these indentations on the other side of the FFC. But if you have got a combination between gold and tin, on the other side, you can see that you've got an area which is a bit more critical. Yeah, and if you apply, or if you do or perform the same test, the salt spray test, you can see here, here a bit more closer look on that, the surface gets deteriorated of the tin, and that might create a bad interconnection over the time. So to make it a bit more reasonable or graphical, it might be critical, but we also need to take in consideration that it is a rough environment. You've got salt spray, it's an addition of water, and salt is a medium, and in combination with a voltage that gets applied, a higher voltage, in this case 1 amp per pin, it's an explanation why you have got this reduction of the tin. So exactly, so explanation why you do use different metals. It is shown over here. It's a question of the price. Of course, nickel is a material which has got, in comparison to different copper alloys, a higher price. Tin is also more expensive, together with copper, beryllium, silver, as an example, also has got a higher price, and the price of gold, it's not shown on that screen. So if I have a look on the time, It's around 40 minutes that I was already talking. And I would suggest also some information from my side. You will get given a link where you can download the presentation. On the last slides, it's just some things that you should or could remind. You've got reason when a tin gets chosen. On the next slide, what are the benefits or the main characteristics on the positive and also on the negative aspects, nickel and gold and so on. But if you do have got questions, please get in contact with me or with the responsible FAE in your sales region. So I would suggest to go to the questions that you do have. Maybe also Markus can have a look on the questions that occurred during the presentation.
Yeah. So first of all, thank you, Florian, for your interesting presentation. Yeah, as you have mentioned, now we would like to turn our attention to your questions. And if you want to send us a question, you can do that with the chat function. You will find that in the webinar control panel. Yeah, as we saw, we already got some questions in the meantime of the webinar. So then let's just start through the different questions. Florian, so first of all, I am concerned with the contact force caused by the fastener bolting a bus bar onto a red cube bolted connection. We have been using Belleville disc springs to maintain the contact force to greater than 15 nano than for square millimeters. Is that sufficient?
Wow. Honestly, sorry, in this case, I'm a little bit struggling with the vocabulary. That it honestly would be great if you if I could answer you that question separately. I think it's more about the press fit connection that you have on one side of a red cube, and on the other side, a copper bar gets attached with a certain torque. I hope I understood it in a correct way, but maybe it would be great if we could talk about that topic in separate email. Sorry for that, but the talk needs, yeah, sorry. Maybe if I read that answer and can go into the in contact with the person who asked that question, it's a bit clearer. Sorry for that.
Yeah, then let's just go on with the next question. So just to be clear, if we can't answer your question now in the live webinar, we will answer it later on via email. We have all your questions which you send us in, and we come back later onto you via email. So then just the next question. Do you have products that combine aluminium wire and copper crimp pins, for example? And how can you mitigate galvanic corrosion?
Okay, so no, we do not have got products like these. Aluminium is often or quite often used for aerospace applications or aspects where you do have got a very, very low contact resistance or very good conductivity. But at the moment, we do not have got products like this in our portfolio.
Okay, thank you very much for the explanation, Florian. Then let's go on with the next question. So what would be the resistance contributors connecting stainless steel to stainless steel?
Stainless steel to stainless steel. Good question, because we mentioned that in the presentation. Stainless steel in our portfolio is used for tactile switches. Tactile switches, we have got a dome or the contact in between that is made from stainless steel, where you do have got a silver plating on top of it. That is the only material that we do have got. On the other side, yeah, it's the only material that we have on the market. Need to check what kind of other materials or connectors use stainless steel, but it's not used that often. So it's more related to switches.
Okay, thank you very much. Then here just a short question or something to remain. Could you explain A-spots again?
The A-spot or an A-spot is the combination. Maybe I just go some slides back. Sorry, by sharing the monitor. Just move that and that. And go to the slide. Markus, you already shared your monitor.
Yeah.
So an A-spot, it was given over here. Okay, just start the presentation and switch the monitors. So what you can see here is the contact zone. If you contact a female and a male contact with each other, in between the A-spots get created. So here on top you have got, in that example here, the connection of the male contact, which is shown here in orange, and or in more yellow color, and in orange it's down below. You can see the contact of the male connection, and in between you create or you get the so-called A-spots, and these A-spots are the sections or the connections between the male and the female part, where you attach the male side and the male side down below, and the female part of the contact or the contact zone, and that is called A-spot or A-spot. And through these A-spot, the electrons flow if you apply the voltage or the current.
Okay, thank you very much, Florian. So then we have another question here, which is regarding just the main thing about the webinar. So someone asked, do I get a review of the presentation? Yeah, in the next few days, we will send you another email and you will get a link there to the presentation as well as to the recording of this webinar. So you can also go through the recording again. So then regarding the time, yeah, Florian.
Yeah. I just wanted to say one thing that came to my mind, where we do have got a contact between stainless steel and nickel, and that is for the shielding of USB connectors, for example. Here we do have got a stainless steel in combination with a nickel plating, and if you think about a connection between USB-A type, male and female side plug and receptacle, in this case about the shielding, we do have got a combination of stainless steel and nickel plating, and that's also a reason why it is mentioned. So that's just one thing that came to my mind and that I wanted to add. Okay.
Okay. So then regarding the time, I would say last question, Florian, then I would say, is galvanic corrosion only a concern when dissimilar metals are in physical contact?
Yep, to make it short, yeah, that's an aspect. Also, what you need to take in consideration is the environment. If you do have got an environment where, for example, some moisture might occur, or you've got a moist environment in combination with a higher current that you apply, these galvanic corrosion might be more critical. If you think about applications where connectors are used inside a building, for example, it's less critical, honestly. And for sure, a lot of customers do use combinations between male and female contact with tin and gold. It's true, it happens. We need to mention that, or also take it in consideration. But it's also some aspect that you might think of. Also about the hardness that we've seen. Tin is much softer in comparison to gold, and if you've got an interconnection between male and female side with two different contact plating, the deterioration or the number of mating cycles gets reduced in a strong way. because of that different material hardnesses.
Okay, thank you very much for the explanation, Florian. So yeah,
Welcome.
now we are finished with our webinar. I see there are a lot of questions left. As we have said, we will answer all that questions via email later on. And if you have any questions left after the webinar, just email us at the shown email addresses. So webinarteam@we-online.com. And we will also try to give you a quick answer there. So thank you very much for your attention. I hope you enjoyed our webinar, and also many thanks to you, Florian, for your time today.
Thank you also very much for the moderation and for you to participate in the presentation. Thanks a lot.
You're welcome. So I hope you will hear us at our next webinar, and I wish you a good day. Thank you and have a good day. Bye.
Bye.